Okay, so let's see, rational exponents. So let's see. So rational exponents, or let me turn the lights off. Sorry. Or basically like fractions. So why do we call it rational? So let's see. Let's just do a little review of the number system. So we know that natural numbers, also known as counting numbers, that's the numbers. Now, IB starts with 0, 1, 2, 3, and so on. Natural numbers, counting numbers, there's a disagreement whether it starts with 0 or not, but we're IB school, so IB starts with 0. The next, and we call that big letter N. The next set of numbers we discuss is integers. Integers are basically the naturals and their opposites. And their opposites. So, for example, we're on the number line, right? We have 0, 1, 2, and 3. What's opposite of 1? Well, that's negative 1. What's opposite of 2? Negative 2. What's opposite of 3? Negative 3, and so on and so forth. So in set notation, we're like dot, 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 negative 3, negative 2, negative 1, 0, 1, 2, 3, dot, dot, dot. And the letter we use for this is Z, which is German for Zahlen. You use it, get that fun fact however you want. The next set of number we're going to talk about today is rationals. The rationals. Whoops. TIO. Rational numbers. It's basically a ratio of P to Q, where P and Q are these integers. We have a denominator, so obviously Q can't be 0. It's basically like your fractions. It's fractions. It's fractions. And because it's a quotient, they use big Q to represent that set of numbers. Okay, so first of all, every integer, every natural and integer can be written as a rational number. So for example, if I gave you the number 7, we could write that as 7 over 1. If you recall, we needed this when we did the equations of lines and slopes, and so we took the number 7, wrote it like 7 over 1. We could do it with negative numbers. For example, negative 3, it becomes negative 3 over 1. And that's the idea. So every natural number, every integer can be written as a rational number. And then the other thing is, fractions as decimals, just a refresher. So for example, either they terminate or they repeat. Or not fractions, let me change that, rationals. It says in rationals at rationals as a decimal. Either they terminate or repeat. So for example, 1/2, it becomes like 0.5, 0, 0, 0. We don't care to count the zeros. But if you do like 2/3, it's like 0.6666, and then you use that symbol, 0.6 with the line on top, which I hate, but whatever. And then the trick you might have learned, maybe you learned a little trick. The trick was the trick is if you have a repeating, let's see, the trick. If you have a repeating number, you can just stick it under like the number of digits over 9. And so you can go back and forth. So for example, and not really, just something to know. For example, I gave you 0.23 repeated. Can you see that? Yeah. You can say, 23 over 99. That's how you write this as a fraction. Or, 0.418. You can say, 418 over 999. And that's how you turn a a repeating decimal to a fraction, and how if a fraction is over the same number of digits of 9, it goes to a decimal. But you have a calculator, so this is fine. You don't need this. The question is, let's see. The question is, let me move the screen over. I'll erase this. Can fractions? The question is, so we're in the exponents unit. So the question is, can fractions be exponents? So can fractions or rational numbers? I mean, but as far as we know it, a fraction is a rational number. A rational number is a fraction. That's going to change a little bit, but I'm just going to use it interchangeably. Can fractions be exponents? Be exponents, and the answer is yes. We can put fractions up in the exponents. So, for example, and they represent roots. They represent roots. So what you see in the book is, so for the first thing, let's just start with the basic. X to the 1/2 is actually the square root of x. And you can check this out in your calculator. If you do like 25 to the 1/2, that's 5, because 5 times 5 equals 25. So this is the square root of 25, which is 5. 49 to the what? To the 1/2. So you say, oh, you know what? That's the square root of 49. That's 7. Once again, use your technology if you're a little weak on the arithmetic. What else? So can we do other roots? Can we have other fractions? Well, yeah. X to the 1/3 is the cube root. So, for example, if I take 8 to the 1/3, which can be written as the root with a little 3 inside, that's actually 2. You can see that from your calculator. It's 2 because 2 times 2 times 2 is 8. Because 2 times 2 times 2 is 8. How about, what else do I have here? How about, can we do other roots? Yeah. How about a 32 to the 1/5? What is 32 to the 1/5? Well, you say, okay, well, it's the 5th root of 32. What times what times what times what times what gives me 32? Oh, that's 2. Or use your calculator. But once again, this is the fifth root. And this is 2. We're going to try to stay in the nice world of exponents. So your powers of 2 to the 2, 4, 8, 16, 32, 64. Your powers of 3, 9, 27, 81. Powers of 5, 25, 125. Other powers of 10, 100, 1,000. Let's go on. Next. So we have regular roots here. Let's see. Okay. The question is, let's get a little more advanced here. Let me erase this. So the question is, good. So what happens if we take it up a notch? For example, I asked you 16 to the negative 1/2 power. Well, the rules don't change. That negative is still a negative. For me, my first order of business, just get rid of that negative. Rewrite this as 1/16 to the 1/2. And now I have positives. You can see a running theme here. Try to get rid of negatives when you can. Well, this is simply 1 over the square root of 16, which is 1/4. Generally, it's just the positive root. Unless it's indicated otherwise, it's generally positive. Let's see, what else do we have here? How about a 1,000 to the negative 1/4? Well, once again, that's 1/1000 to the 4th, which is 1/10. No, sorry. 10,000 to the 1/4 is 1 to the 10. Sorry about that. Check your GDC. Once again, the rules don't change. The rules don't change. Now, and then you might be asked to write it in index form. So for example, if I give you the square root of 7, how do we write something as summing to an exponents? Well, immediately you're like 7 to the 1/2. What if you see, I don't know, 5, the 5th root of 82? Immediately, this is 82 to the 1/5. How about, 1 over, radical 3? Well, immediately that's 1 over 3 to the 1/2. And maybe that becomes 3 to the negative 1/2. Once again, the rules don't change. It's just different forms. We're just exploring the different representations. That's it. Let's take it up a notch. This is the advanced part. This is 10. This is 10 advanced. But you know what? I think you guys can do it. I think you guys can do it. Or everyone can do it. Let me move the screen over. Da-da-da-da. Okay. Now, if you notice, every single fraction has something like 1 over something. The question is, how do we deal with x to the m over n? Well, the books, you're going to see it like this. It's the nth root times x to the m. You might see it like that. What's going on there? Well, let's hold off on this for a second. What we're going to do is we're going to rewrite the m over n as 1 over n times m. Because if you recall, when we have a power to a power, we multiply them. So we're going to do the opposite. And all of a sudden we have the nth root of x. Let's do an example. How about 4 to the 3 halves? 4 to the 3 halves. That's kind of weird, right? 4 to the 1.5. Well, it's a fraction. And the square, so immediately we're going to rewrite this as 4 to the 1/2 cubed. Well, I like 4 to the 1/2. If you don't have a calculator, this is what you're going to say. So, for example, you'll see 2 to the 3rd, and this is 8. Let's look at another example. How about 125 to the 2/3? 125 to the 2/3. Okay, I'm going to break this up into 125 to the 1/3 times 2. Nice, I like 125 to the 1/3. This is 5 squared, or 25. How about 8 to the 5/3? That's kind of weird, but it's not. Let's just break it down and see what happens. Once again, you should start recognizing these numbers. The 4, the 125, the 8. These power. Let me change. You know what? I'm going to change this to a. I don't know. Let me change to 27. 27 to the 5/3. So you're like, okay, the sum is first 27 to the 1/3 to the 5th. Okay, 27 to the 1/3. That's 3 to the 5th. And that is what? 243. So it's a little advanced, a little mental math, or you can use your calculator if you need it. And then the idea is, can you write it using index? So for example, if you see, the 7th root of, m to the 9th, how do you write that using indices? Well, once again, this is m to the 9th. To the 1 over 7, final answer, m to the 9 over 7. It's just, once again, just going back with these rules. And then one more, just to simplify this. So this is, write using indices. And then the last thing, once again, let's just do a roll. Let's just bring this all together. Last question. How about 100 to the negative 3 over 2? What are we going to do here? Well, personally, just start with that negative. 1 over 100 to the 3 over 2. Next, 100 to the 1/2 cubed. It's 1 over 10 cubes, 1 over 1,000, 1/1,700,000. That's basically it. Try the problems in the book. The first group is from the year 9. The second batch is from the year 10. See how you do. Nice.